Good morning, everyone. Welcome to this webinar on industry trends and university engagement opportunities for the powder metallurgy industry. My name is Heidi Shattuck, and I'll be your host for today. To pass the time while we wait for everyone to join the webinar, I'd like to pose a question for our attendees from industry. What percentage of your company's products are sold to the automotive industry? Please feel free to answer in the chat box with an approximate percentage and your company name if you wish to share it. All right, it looks like we're getting some answers to our question. Thank you for that. So I have a few housekeeping items to cover before we get started. All attendees are automatically muted with your camera turned off. If you have any technical difficulties accessing or hearing the presentation, just use the chat pad and we'll try to correct them promptly. Attendees can submit questions at any time during this 40 to 50-minute presentation using the Q&A button. However, we'd like to wait until our Q&A period at the end of the webinar to provide your answers to your questions. This will allow us to move through the material more efficiently. If you have any questions after the webinar, please send them to us via email at pentap@psu.edu. This webinar is being recorded and will be uploaded on the PennTAP website, and all attendees will receive a follow-up email notifying you when the recording is available. On today's webinar, we have guest speakers from 2 Penn State campuses. Dr. Todd Palmer holds a joint appointment as Professor of Engineering Science and Mechanics and Materials Science and Engineering, and he is the Director of the Center for Innovative Sintered Products at University Park. Dr. Palmer's research areas include high energy density welding and joining, additive manufacturing, and particulate material processing. Dr. Daudi Waryoba is an Associate Professor of Engineering at Penn State Dubois. Dr. Waryoba earned his PhD in Mechanical and Materials Engineering from Florida State University. Dr. Waryoba's current research interests include thermoelectrical mechanical processing of metallic materials, powder metallurgy, and additive manufacturing. My name is Heidi Shattuck, and I'm a technical advisor with PennTAP. My role is to help build and manage relationships between Penn State University and small to mid-sized businesses in Pennsylvania. First of all, in our webinar today, I'll describe ways that PennTAP can help identify no-cost and low-cost ways to improve your business through our direct technical assistance, referrals to our resource partner network, and engagements with Penn State students, faculty, and facilities. Then we'll be joined by Dr. Palmer and Dr. Waryoba to discuss industry trends and university engagement opportunities for the powder metallurgy industry. Finally, we'll end with a Q&A session. So let's get started with a little bit about PennTAP. The Pennsylvania Technical Assistance Program at Penn State, known as PennTAP, is a statewide technical assistance organization charged with supporting Pennsylvania businesses and anchor institutions, including manufacturers, municipalities, educational institutions, entrepreneurs, and economic development agencies. We began over 50 years ago as one of the first technical assistance programs in the country. PennTAP focuses on helping Pennsylvania businesses through 2 primary areas of expertise: energy and operational assessments, and university connections. Through these pillars, our goal is to help your business be successful and drive economic growth in Pennsylvania. You can find more information about us at pentap.psu.edu. PennTAP has a diverse staff with backgrounds in chemical engineering, electrical engineering, environmental science, management, and economics. Our staff includes a certified energy auditor, certified energy manager, registered environmental auditor, renewable energy professional, a professional geologist, and a Six Sigma Green Belt. Through our energy and operational assessments, PennTAP's technical advisors perform pollution prevention and energy efficiency assessments, also known as P2E2 assessments, where we help companies decrease pollution and increase energy efficiency. E3 assessments build on E2 assessments by incorporating lean manufacturing into the process. The U.S. Department of Energy's ISO 50001 Ready Navigator program enables companies to implement a tailored energy management system, which provides the framework to integrate energy efficiency into your existing management systems. PennTAP is one of a small group of organizations recently selected by the DOE to provide training for this pilot program to a cohort of manufacturers. We also offer Penn State graduate students in the College of Engineering opportunities to gain hands-on experience by having them assist us with our energy assessments. These students often utilize the knowledge they're gaining in the classroom to bring new ideas to our clients. And beyond energy, we work closely with our clients to understand the full range of their business needs and facilitate innovation by creating connections back to the university and our vast network of resource partners across the state. PennTAP can provide your business with no-cost and low-cost opportunities to engage with Penn State students, faculty, and facilities through internships, capstone courses, classroom projects, and research partnerships. Penn State classroom projects and capstone courses provide great opportunities for companies to tackle complex problems using classroom knowledge and world-renowned facilities. PennTAP has enabled connections to the university for a variety of industry-sponsored projects, including product development through prototyping at the Learning Factory, improved production flow through Six Sigma student projects in the industrial manufacturing engineering classroom, and growth into new markets with market research completed by the Smeal College of Business Nittany Lion Consulting Group. PennTAP is currently a partner on a grant project funded by the Arc Power Initiative. The grant is focused on igniting innovation in the PA Wilds region. PennTAP is using a portion of the Arc Power grant funding to offset the sponsorship fees for the Learning Factory, which would allow a select number of industry sponsors to take advantage of this resource at no cost. PennTAP also works very hard to connect our industry clients with research partnership opportunities, such as the Manufacturing PA Innovation Program, which is a collaborative effort between state government, academia, and industry to drive new technologies and processes in the manufacturing sector. One of our guest presenters today, Dr. Waryoba, was recently awarded grant funding through the Manufacturing PA Innovation Program. He and his team have partnered with Simco, a manufacturer of powdered metal parts, to research innovative new technologies for the automotive industry, which he will describe later in today's webinar. The Small Business Innovation Research Program funds small businesses to stimulate technological innovation to meet federal research and development needs and increase commercialization. PennTAP's direct connection with Penn State researchers allows us to make the right connections to faculty for small businesses to meet the requirements for university participation in this program. PennTAP maintains relationships with a wide range of resource partners throughout the state. These resource partners bring different tool sets to complement PennTAP's suite of services. Our resource partners include small business development centers, industrial resource centers, Ben Franklin Technology Partners, local development districts, and others. With technical advisors in every region of the state, PennTAP can help you make personal connections to the economic development representatives working in your area. Our relationships with these partners are vital for Pennsylvania businesses. In 2020, we helped 105 companies in 36 counties throughout Pennsylvania to save a total of $2.5 million, and we helped to create or save 29 jobs. But the greatest measure of our success is the testimonials we receive from our clients. Please feel free to browse the success stories on our webpage to see lots of examples of how PennTAP is benefiting Pennsylvania businesses. As I mentioned earlier, one path to innovation that PennTAP follows is making connections with Penn State faculty in their groundbreaking research. I will now turn over the webinar to our guest presenters to discuss industry trends and university engagement opportunities in the powder metallurgy industry. First up today is Dr. Todd Palmer. Thank you so much for joining us today, Dr. Palmer.
Oh, thank you, Heidi. I'm just gonna, one too many, there's a little bit of delay there. So good morning, everyone. My name is Todd Palmer, as Heidi said, and I'm a professor at Penn State. And what I wanted to do is spend a little bit of time here and hopefully not too much of giving a brief overview of some of the facilities we have at Penn State that we can direct primarily at really powder metallurgy and materials characterization. I'm going to allow Daudi to really hit a little more on the industry trends with his proximity to a lot of the powder metallurgy industry in Dubois. I want to focus on a couple areas at Penn State and some emerging opportunities that we have primarily for some of these industry collaborations. As far as the powder metallurgy industry, I want to focus primarily on 3 institutes and centers at Penn State and a range of the equipment we have. So as we go through here, it may at first seem like I'm just listing all this equipment we have, but I think as you take a look at some of the opportunities that you might see as you start thinking maybe about changing some product lines or improving the processes that you have, that we have a lot of really high-end tools that are available to industry here at Penn State, and I really believe would be very helpful to you, primarily at the Materials Research Institute and at the Center for Innovative Materials Processing through Direct Digital Deposition. I'm going to say SIM3D is really our acronym for that. I'm only going to say the long name once. It's a bit of a mouthful. And the Center for Innovative Sintered Products, or CISP, which has been a little more traditionally the powder metallurgy capabilities within Penn State, whereas SIM3D is really our current additive manufacturing capabilities, and they are using a wide range of different powder products. We'll see that. And 2 new and emerging industry collaborative opportunities at Penn State that I wanted to talk about. The first one is the Manufacturing Materials Joining Innovation Center. This is an NSF, or National Science Foundation sponsored center that is meant to promote collaboration between academia and industry. And it is led by Ohio State, and Penn State is a new member in MAGIC, as you can tell by we have to come up with our good acronyms for all our centers before we get started. And I do want to bring up another one as an emerging opportunity at Penn State to build a satellite Fraunhofer Center centered at Penn State with an emphasis on materials processing and powder metallurgy in particular. So within the Materials Research Institute, there we go. We have really the Millennium Science Complex, and really have to show off the building. It's an extremely large facility. On the left side of the wing is the Materials Research Institute. On the right side is the Huck Institute of Biosciences, Life Sciences Institute. we're going to concentrate mostly on what we have available for industry. And as I said, all of these are available to industry. And what I will sort of say up front is that you have my contact information on the first slide, and I'm definitely available. You can feel free to contact me anytime, and I can direct you to the appropriate people within the materials characterization lab or within some of our other labs here at Penn State. But as you can tell, the materials characterization lab itself is really, there's a bit of a Zen garden here in the front of the Materials Research Institute. And probably 50 to 100 feet underneath that is where the materials characterization lab is. And you'll see why we need to have really these vibration proof rooms, these very specialized rooms in order to handle some of the equipment that we have available. So we do a range of different things. And what I typically like to sort of show to people and to let them see is the areas within the lab that allow us to look at very specific things. We have, for the most part, the optical microscopy, basically microscopes, scanning electron microscopes that allow us to see really grain structure. You start thinking of powder metal parts, this would be looking at a finished part, whether you have a part or a design that might be giving you some issues with premature failure. These types of tools are there for that. And we can go a little further using the scanning electron microscopy and really start looking a little more closely at grain structure. And so really understanding maybe some of the failures that you might be having or process issues that you're running into. We can delve into very, not quite atomic scale with these, but getting close to a really a nanotype scale evaluation of your parts with X-ray diffraction, scanning electron microscopy, and understanding chemistry. And for a lot of the metallic components, we use energy dispersive X-ray spectroscopy. And what it tends to give us are these very informative maps. So I'm old enough to remember days before a lot of these maps and a lot of these tools. And really, I would say in the past 15 years to 20 years, really these tools have really evolved to the point where we are able to probe and find issues and really start to understand things that we've never really had the ability to do with really high precision in the measurements we make. So when we're saying that you have a certain amount of an alloying element at a certain place, we are positive that is correct. And it's a long way from when I was a graduate student back in the early 90s from what we're capable of doing. These capabilities have really grown, and we're really taking advantage of them to understand these. So really what you sort of see here as well is some of the work that I do. I do a lot of work in ferrous materials, whether they are austenitic stainless steels, 300 grade, 304, 316, 310, 308, steels like that. Duplex stainless steels are another area that I tend to look at. And a lot of these tools allow us to identify phases that really are difficult to bring out just in optical alone. So we're really able to delve much deeper into some of these materials characteristics and things that, you know, really, if your internal labs don't have those capabilities, we have very affordable and very easy ways to work within to take advantage of a lot of these tools. And if you really want to get fancy, you can get into transmission electron microscopy, and we can look at, you know, atom layer type things. You start seeing that we're characterizing oxide inclusions. This is in a nickel-based alloy that is shown here. And really what it allowed us to do here in this image was to resolve dislocations across the material. These are small defects in the metallic systems, and really understand how a precipitate grew off an oxide inclusion that existed. And this is from a powder part. This is an additively manufactured Inconel 625 component. And it allowed us to really start to understand how microsegregation and melting and all the things we do in additive that you're not supposed to do to metals, but we do anyway, and allows us to really see that. And so there are a number of different transmission electron microscopes on campus, and some of these are pretty large. I don't think this really gives you an idea of how big this system actually is. And these are allowing us to have really that atomic scale resolution. of what we're looking at. We also have mechanical testing capabilities, and really one of the more interesting things that we use mechanical testing for is rather than just pulling tensile bars and looking at an engineering stress strain diagram and trying to measure yield and ultimate tensile strength and ductility and elastic modulus, we use digital image correlation. So we actually will paint these specimens and use some higher end image analysis to allow us to look at localized strain that occurs. Now, when you have different transformations in different materials, we use this widely within my group to understand really plastic deformation and really the role of potential defects, porosity, lack of fusion, types of things that you run into in additive manufacturing processes. And so we use a lot of these tools, not quite daily, that we don't have quite that much time to do. It takes a lot of time to analyze these, but we can really start to look at how materials are behaving at a much more fundamental level. And from a failure analysis standpoint and a process understanding, these tools are really almost invaluable at this point. Micro and nano indenters, this has gone a long way too. This is a lot beyond what you might have used in school, or the micro hardness indenter, the manual micro hardness indenter. The micro hardness indenters we use basically map out entire hardness maps of surfaces. And so it, for the most part, uses CNC type tools to lay out a map and gives us an entire, we can pretty quickly over the course of an hour or two take a look and characterize the hardness across fairly large areas. We can also do nano indentation. This allows us to go in and look at really fine areas, so much smaller than the Vickers or Knoop or Brunel hardness measurements that you might be used to taking. We also have been growing in a lot of this powder feedstock characterization. And I will say it's something that I never really thought of before I got into really a lot of the metal powders, particularly in the additive manufacturing realm. But we have typically your master size or your Malvern system for laser diffraction measurement of particle size distribution. We also do a lot with particle imaging and image analysis. And we go a little bit beyond this to allow us to start to get morphologies of powders. But the other area where a lot of these tools are used, and I had never really thought of it, is in the food. A lot of times we have, as you can imagine, with our proximity to Hershey and whatnot, we have people who do work in chocolate with the creamery. And a lot of those research groups over in food science use a lot of these tools as well. So we're really sharing that, and the shared facility that MRI provides us really helps us to build some of these other capabilities. And so from powder feedstock characterization, and most of you familiar, if you have particle size distribution measurements in your labs are available. We look at them in a number of ways. Now, in the image analysis side, we're really interested in how particles change shapes, whether they're gas atomized, powder particles, and all of these are just 4 examples out of a single lot of powder of how particle size can change, even under gas atomization. We go from where we think everything looks like spherical to really what some of the other particles look like. So it gives us really that understanding of how the powders are impacting some of our additive manufacturing processes. We also have mercury porosimetry, helium pycnometry, and one of the more interesting things that we do is really this is a higher end research type topic, but I think it'd be of interest to industry as well, as our capabilities within the Center for Quantitative Imaging, where we do, for the most part, for lack of a better term, is CAT scans for metals. And what we in my group have done is looked at powder particles and looking at fairly large areas of powder particles, of understanding how they change in shape. But more interesting is how they can have differences in internal porosity and being able to characterize that internal porosity. Now, when we're looking at some of the other things we do, particularly in terms of powder rheometry, these differences in porosity become really important for us. And so those are some of the areas that are within the Materials Research Institute, the Materials Characterization Lab at Penn State, those are all open to industry involvement. They have special contracting procedures for having you come in. Now, the center that I'm involved in is a little more geared at really sintered products and powder rheology and some other things. Here, what we show is one of our other capabilities is spark plasma sintering. And we have a fairly significant capability of that here at Penn State, as well as in a quenching dilatometer that we have, especially, which would be especially valuable in a lot of the ferrous type products that you may be producing. And we are really delving into the idea of looking at new methods for characterizing powder feedstocks, and particularly in what is called powder rheology. We have the typical characterization techniques, and we go through those. But in powder rheology, what we're really trying to understand is how powders are behaving a little bit more like fluids in larger scales, and looking at tests that are more indicative of what a powder might be going through, especially in the additive manufacturing field, where we're spreading a powder with a blade, or we're running powders through nozzles and feeding them into molten liquid pools to build up parts. And so we have capabilities here at Penn State for different types of techniques. And so they go as simple as a rotating drum, which is really just an image analysis system of rotating a powder mass with a camera and measuring avalanche angle, to powder rheometers, where blades and torque meters are used to measure the torque required to move a blade through a powder, or a shear cell, where we can measure permeability and other types of packing and void space type techniques. And we integrate this a lot of times with the computed tomography or the X-ray CAT scans capabilities that we have, to really understand how they all sort of break together and give us a lot more insight into what's going on with the powders. And so wanted to just run through of how we use a little bit of these in the rotating drum. As we measure basically avalanche angle, and this tool we found is really good at characterizing powders in terms of how they're going to operate in a powder bed fusion system. The powder rheometers are much better at telling us mechanical blending of powders, something that you would see much more in an injection molding type system, where you might be moving a powder through with a screw driven mechanical mechanism, which is very similar to what you see in a thermal spray or a directed energy deposition type powder feeder that we have available. So as we move on here, our quenching dilatometer is another capability. And I always like to show this because this tells us a little bit more, not only of phase transformations, but of starting to understand a little better and doing very high resolution measurements of thermal expansion. We're seeing, particularly in the additive field, as we additively manufacture different components, their coefficients of thermal expansion are not well defined. And so we can take small specimens, and these can originate from a powder, rot, whatever type of material you want, heat them up at very specific rates and cool them at very specific rates. So you see this liquid nitrogen, we can go down to about a negative 150 degrees C. So we can start understanding transformations and transformations of martensite through cryogenic heat treatments that you may be applying to different parts that you have, and starting to understand a little more of what's going on within the material, and maybe catching some things that you may not be able to see through more traditional techniques. And these are some of the high fidelity. And this is an example of one technique we use to really start to understand how different compositions, and what this is really sort of showing is one of the real areas within the additive manufacturing field that is of interest to people is what are called functionally graded materials, where we can change compositions on demand. And that's all well and good from a design perspective, but as many of you in the processing and manufacturing industry know, sort of when per se the rubber hits the road, these different compositions have different coefficients of thermal expansion. And the minute you start heating them up and cooling them down, they start to fail. And so understanding that is one of the areas where we're looking at. And we've done that and measuring it, and you see some example curves there. Now, the Center for Innovative Materials Processing through Direct Digital Deposition is our AM center. And they're arranged. I'm just going to quickly run through these to leave a little more time for Daudi to go. Now, the AM parts, if you listen to the hype that's out there, there's a perception that it's going to change everything. It can do everything. These different techniques don't. And if you have an interest in AM, I'm more than happy to talk a little bit more about some of the additive manufacturing and what the capabilities are that are out there. But we have a range of capabilities at Penn State, from the powder bed fusion to do the real fancy stuff, that the showcase type things, up to repair large parts, things that are a little more industrially relevant. And as I said, we work in both these systems, and they're both powder-based systems. And for the most part, in the additive manufacturing field, for sort of the lack of a better term to say, is you have a lot of people working with metal powders who don't really know a lot or understand a lot about metal powders. And so there's really a need within the additive manufacturing industry for people who know how powders are going to behave and how they're going to react and flow and different things like that. Now, we've been working in the area for probably about 25 years, from laser cladding to deposition type processes. And we've built some of our own system. This is what might be considered a home built system for directed energy deposition. And we have it integrated with a 12 kilowatt laser. We've done about any material you can imagine on this. I would say from magnesium, aluminum, to titanium, to any type of steel that you can imagine, to nickel-based alloys, to titanium. Molybdenum was deposited on this system. Tantalum's a possibility because nobody wants to pay that much for all that powder. But it gives us a wide range of capabilities to build larger components. We're also working with robotic systems. So there are robotic systems available. These are typically tend to be wire-based processes. It's very easy to integrate a gas metal arc or a MIG torch, if you will, onto a robotic head and allow you to build up fairly large parts. And so we have that capability here at Penn State as well. Give you a little bit of picture of what it looks like. And then sort of these wire arcs. So they come up with people came up with the acronym. They call it WHAM. I tend to think of the 80s pop band every time they want that. So I want to put an exclamation point behind it. But I don't think a lot of the people who came up with the WHAM acronym really appreciate that. But it's gives us those other capabilities. So you can sort of see the wide range of abilities that we have within Penn State and where the powder industry comes in there. Now, as far as industry collaborations, I want to bring up two in particular. The Manufacturing and Materials Joining Innovation Center, MAGIC. Now, what NSF, or National Science Foundation, has done is they've developed this concept of these centers where you can conduct research. And so there are a range of universities in there. So this gives us access to not only that school in Columbus and Ohio State, but Lehigh, Colorado School of Mines, University of Tennessee, Knoxville, the University of Waterloo is in Canada, and Penn State are all members of this, with thrust areas in a number of industrially relevant areas. So there are 48 industry members, and you start to see just from the insignia of the wide range of people who are involved in the center, from national labs to materials producers to end users to DoD labs. So it gives you a wide range. Now, the annual membership dues are there. This is really meant for larger type companies, but there are small companies. Thermocalc is a small company, and there are opportunities for in-kind contributions. And the way the center, I can provide you with more detail on how the center works if you have an interest. It's really there to promote the development of this fundamental knowledge. Now, all of these programs and any programs that the center runs are industry directed. So there's an industry partner, an industry mentor, and this is a great way to find students at the master's and PhD level without having to really go to career fairs and worry about how I'm going to get hundreds of resumes. You can get really directed recruitment through this type of center. Now, the other potential, and this is one that is being built up, is the Fraunhofer Institute is a German institute, but they have a USA Institute Center, and there are a number of university partners. And Penn State right now is in the process of looking at a satellite location for Fraunhofer and building an institute based a little more on materials processing and powder metallurgy as one of those areas. So the other centers that are there, there's definitely a need as we start thinking of reshoring and with the pandemic and the supply chain issues and really an interest at the federal level for manufacturing, that it is available. And so within the Fraunhofer system, if you're not familiar with it, it's the German Institute. It is highly successful in Germany of really being able to build relationships between universities and industry and government. And what it allows a lot of things to do is really go over what we consider this valley of death here within the innovation cycle, of going from nice things that universities might do into things that are actually products, and working through a lot of that. And there are opportunities to partner, and Penn State right now is looking for potential companies to partner with on developing this type of model. So at that point, I'm going to turn it over to Daudi, and thanks a lot for putting up through a lot of that. So, but once again, if you have any questions, do feel free to contact me about that. So I'll turn it over to you now, Daudi.
Thank you very much, Todd, for extensive coverage of the capabilities and opportunities at Penn State. Ladies and gentlemen, my name is Daudi Waryoba. I am Associate Professor at Penn State Dubois and the coordinator of the 4-year Engineering Applied Materials. And as a satellite campus, we too have full access to all the facilities at the main campus. So any of the capabilities that we don't have over here are supplemented by what Professor Palmer has highlighted. Our campus is very fortunate to share a healthy symbiotic relationship with our local industries. We usually provide them with technical assistance, and they can use our equipment for free. And in return, they supply us with most of the materials. And whenever we want to process our specimens with industrial settings, they usually don't hesitate to give us time in their busy schedule. And for that, I thank you very much. And I know several of the participants from our local area industries. I really thank you very much for the assistance and support you have been giving our program. So as you know, we are at the epicenter of the powder metallurgy industries. And yeah, about 70% of the PM products are used in the automotive industry. Most of these materials are iron-based parts. And for that matter, the forecast from the sector of the PM industry, very thankful for MPIF, is showing that there is a PM volume sales and shipment will continually decline with increasing tight emission control and electrifications. I mean, we know how much of these values. I'm still waiting for the control 80. Yeah, so due to this tight emission control, we are expecting a trend, a declining trend in terms of the PM volume sales. And the data is showing the electrical vehicle market alone is expected to soar to about 5 trillion by 2030, with investment going up to 330 billion between 2021 and 2025. So you can see this is not something which can be ignored. The PM industry has to jump into the wagon. So today, what I'm going to highlight is a few projects that we have been doing collaborative with our local area industries that are focused on automotive parts. The first project is on the, oh, sorry. Yeah, so the first project is on the code sintering for high performance powder metal parts. This is a project which is the lead investigator is by Dr. Makrishna Rajagopalan, and the current collaborator is Horizon Technology Inc. And it has several potentials, including cementite carbide, soft magnetic and soft magnetic composites, green machining, densifications, and high strength sintered parts. This is one of the projects that was also funded in 2020 by the PA Manufacturing Innovation. Now, code sintering is something which was adapted, okay? It's a mechanism, it's a process which was adapted from the work by Professor Clive Landos at MRI, Material Research Institute. They work on ceramics. So they've been doing a large work on code sintering of ceramics. So Professor Rajagopalan thought this is something which we can also try to see if we can apply this method for metallic materials. So it's called sintering because actually for ceramics, this can sinter ceramic materials at relatively low temperatures. So in the case of metals, of course, we don't expect them to be sintered at that low temperature. However, this method gives you properties which are extremely much better in a compacted parts. So if you think what happens during the code sintering process, this process, okay, which is done usually under pressure and temperature, of course, over time, is showing you there are several stages, okay, but what you find, there are several what we call multi mechanisms with coupling effect from mechanical, chemical. Yes, there's a chemical, what we call usually hydrothermal reactions, which usually happens. So the particles, when you apply pressure and time, you end up having some sort of like a liquid phase between the particles. And this liquid phase, there are several opportunities which can be used, okay? You can use it as a liquid, as a transient liquid phase in the material, in the case of sintering, to give you a much better strengths. Or you can also use, in the case of green parts, you can get better green strengths, which allows you even to do machinabilities. Not only that, if you think about that, you can also use that to create some coating. And that allows you also to think about what we call soft magnetic composites. So there are several opportunities for this project. Now, in the case of machinabilities, we have seen that we can even machine the part. We can make threads for this, okay? We can drill, we can make threads. And if we compare a code sintered part, this is what we call green parts. If you compare a green part, a drilled green part compared to a warm compacted, okay, part, you see that the green parts usually have a much strength. It is intact after the machine, after drilling, compared to a warm compacted parts. We can even do threading of the parts. Yeah. The strengths, the green strengths of a cold sintered part is double what you find in a warm compacted parts. So that gives you several opportunities which you can use in the green parts, even before you sinter the parts, the opportunities are diverse. Now, when you go, as I told you, in terms of opportunities of coating the particles with this method, it opens up opportunities for soft magnetic composites. Not only that, if we go ahead with the liquid phase and everything, we can get soft magnetic. So there's an opportunity for soft magnetic as well as soft magnetic composites from this process. So the opportunities are wide, and we are open for any collaboration from the industries. Yes, at this point, we are right now collaborating with Horizon for this soft magnetic composite, but there are other opportunities which you can use this method. Now, the next project, which I'm also going to share with you, is think about in the automotive parts. Yes, with all these tight emission controls and everything, one of the solutions is actually to reduce the size. So if you think of reducing the size of the engine, at the same time requiring the power, so you are required to have what we call high power density parts, which can sustain both mechanical and thermal loading during the operations. Those are requiring now new way of thinking what type of parts we should have in order to provide this kind of high power density parts. So right now, we are working with SIMCO in order to fabricate what we call some new, materials of copper, nickel, silicon. Most of these materials usually are from rock materials where they are rolled, and before they can be edge hardened. But over here, what we are trying to do is to see what can we do with our PM technology if we can produce some of these high strengths, high semiconductivity and electroconductivity parts, which will be fantastic, which will be very good parts, especially for in the case of connectors, in the case of cylinder seats, cylinder valve. You need those kind of materials which give you both not only strengths, but at the same time in terms of thermal expansion coefficients, wear and friction properties, as well as corrosion resistance. So copper, nickel, silicon is one of those alloys, or what we call possibilities, which can be used in those high density parts when you think of downsizing of internal combustion engines. So what we have right now, we're working with SIMCO, and we have seen considerable properties, better properties of the copper, nickel, silicons. Yes, we are trying to make sure that we can, especially this alloy, the benefits of this alloys comes from what we call precipitations. So the precipitation over here, that's why we're having copper, nickel, silicon, and we're also adding some additional alloying elements like magnesium and aluminum in order to facilitate or to enhance the precipitation method. So with copper, nickel, and silicon, you are going to get what we call the silicides. Those are silicide particles when you're doing what edge hardening. They are the most important in terms to give you the strengths which are required for those high density parts. And at this point, we are showing very promising results. And there's so many opportunities, not only for this, but for other parts, especially when you're talking over electrical components. Now, the next project which I'm also going to share is the diffusion bonding of bilayer silver graphite copper. This is a project which we have been working for some number of years now with contact technologies, and it's showing considerable application now, because now we can use cold sintering technique on the diffusion bonding. We have seen benefits when we are using cold sintering in order to create what we call bilayers, not only bilayers, there's opportunity also to do multiple layers. In the case of copper, graphite and silver graphite composites, what you find, of course, their contact technologies wanted to make sure that they can reduce the cost of silver. Silver is highly expensive compared to copper. So the opportunity to have bilayers or multiple layers of copper and silver becomes much better, cost effective compared to have a contact of only silver. So the bonding between silver and graphite is essential, but having graphite is also a problem. Yes, graphite gives you what we call wear resistance, especially for arc erosions. However, it also presents a major problem in terms of bonding of the two parts, the silver and copper. So throughout what we have worked, we came up with what we call an interlayers, and we have seen better interlayers which are working, and with now called sintering technique, we are getting better results. This opens up for a variety of opportunities, not only for electrical contacts. You can see the opportunities to have what we call as a multi-layers of with different properties, mechanical, electrical, magnetic properties, thermal properties, or you can even come up with what we call functional graded materials using these techniques. So the opportunities are wide, and we are still exploring, and we are open with industries. There are so many opportunities throughout this method. Now, the last but not least, of course, we are also working with North American hardness, and over here, constituents, what we call microconstituents of, especially with steel alloys, is very important. It's usually very important to understand what percentage of what is martensite or bainite, austenite, what you have in the materials, because they all affect the mechanical properties and other properties of the materials. So having a better quantitative method of characterizing the structures is fantastic. So we are using over here not only some of the equipment we have, the same thing as Professor Palmer showed you, the equipment at University Park, in order to quantify especially how much austenite, retained austenite do we have when we're talking of bainite. What in terms of, okay, lower bainite, upper bainite, okay, how much pyritic structures do I have? How do that affect the material properties? So most of the steel, the PM steel materials we have over here is always those microconstituents that affect the mechanical properties. And now we have an X-ray diffractions, which will now help us, especially to be able to get those residual strains in the materials, which you can also quantify and correlate even with how much of the retained austenite we have in the materials. So I know Daudi is anxious for me to stop here so that we can allow participants to ask you questions. But in case you have any question, do not hesitate, okay, to contact me or my colleague, Professor Rajagopalan. Okay, we are open at any time to collaborate, to work with you, with your ideas which we have. We can also help you to come up with even new production lines. Thank you.
Thank you so much to Dr. Waryoba and Dr. Palmer. Those were really, truly fascinating presentations. I just learned a whole lot in a short amount of time. So if we can just take a minute here to get through some Q&A. We have at least one question here in our Q&A box, and this is coming to you from Eric Wolf, and he's asking, could you please speak to your capabilities to characterize magnetic properties of powder metal materials?
I'll defer to you on that, Daudi. I don't really have too many capabilities in that area. It's definitely an area that we're interested in getting into. But right now I don't have anything. Probably have a better answer in about 6 months.
Yeah, thank you, Todd. And actually, yeah, Eric knows, yeah, this is something we have discuss, and that's something which we are really trying to make sure that we can have these capabilities in the near future. Yeah, because this is very important in order to be able to get the properties of the soft magnetic or soft magnetic composites which we're trying to make. So at this point, I don't think we have the answer to you, Eric, but we will soon be able. We are in the process of getting procurement. I mean, getting all the necessary information before we can procure the equipment. Thank you.
Okay, great. And it looks like we just got another question through the chat. So let me find that. This is from Joseph Hackett. It says, we are looking at 3D printing options that would help us connect education to manufacturing who are looking for parts, either as a result of supply chain interruption or reshoring, and need help identifying the options we should consider and why. Thank you in advance for any help available.
Yeah, I responded quickly to Joseph in the chat on that. I'm not sure it went to, did it just go to the host, or I don't think I sent it to everybody. So I think I messed that up.
Says it went to hosts and panelists.
Yeah, I'm seeing that now. So I'll just see if I can copy and paste it in. So I would say that's a fairly complex question. There are a lot of moving parts to that type of question, because it's really going to depend on materials, applications, part size, different things like that. Probably I can give you a little more idea of some of the options we have. Feel free to contact me directly, and I can run you through what we have and what maybe some options are for you.
Okay. Thank you, Dr. Palmer. Okay.
I think there was another question in the chat from, I think,
I see
Phil.
that. Yep.
Phil.
From William Edwards to Daudi. Can you explain how cold sintering is used with SMC material processing? I have watched Penn State videos on cold sintering and do not understand how it could work with SMC.
All right. I don't know if I can go back to the slide.
I think if you just click your mouse, you should still have control.
I still have the control?
You should, yep.
Okay, I'm requesting your control. So,
okay, yep.
So Bill, it's good to hear from you, Bill. Thank you very much for all the MPIF support we have been receiving. And yes, to answer your questions. All right, so at this point up over here, Bill, we are working with Horizon, and yeah, I don't want to spill much of what Horizon is now trying to do with our process. But however, as I told you, as I've mentioned, okay, the possibilities of having, creating a specific coating, because for soft magnetic composites, you're trying to create a coating on the material. So there is, yes, you can utilize. Now at present, if you know, okay, most of the PM, they are using, okay, soft magnetic composites are usually done as I use utilizing oxidation. So steam is one of the methods which they usually use to create a coating in order to get this insulation between the particles. So over here, you can see with cold sintering, there's a possibility of creating a coating, and you can tailor-made the type of coating which you want, okay, to give you. So that's why we have the possibilities are higher. And as I say, I don't want to spill everything what Horizon is right now trying to do with that method, but this is something which is doable, and we are still working on it. And at the point when Horizon will be ready to share this information, I'll be happy to do that. Thank you.
Okay, wonderful. Thank you. I don't see any other questions at this time, but please, just as a reminder, if you have questions after the webinar, you can reach out to me or either one of our guest speakers by email. So just to wrap things up today, I'd like to offer a couple of key takeaways from today's presentation. And first of all, I think it should be apparent at this point that Penn State really has some state-of-the-art facilities that are open to all organizations to utilize. Also, by participating in Penn State research centers, you can share in the development of new processes and products through sponsored research opportunities, and it gives you an opportunity to interact directly with Penn State faculty. And finally, PennTAP's goal is to help you grow and sustain your business by connecting you to this vast array of resources available at the university and really all across the state. Thank you again, Dr. Palmer and Dr. Waryoba, for taking the time to talk with us today. Before we conclude, I'd just like to tell you about a couple of PennTAP's webinars from earlier this year that you may find interesting. Recordings of both webinars are available on PennTAP's website. On July 17th, we hosted a webinar titled Pathways to Smart Manufacturing Through Smart Maintenance. PennTAP was joined by Dr. Vital Prabhu, who described the processes by which manufacturers can begin to develop a smart maintenance program using data and ways Penn State can assist companies with this transition to smart maintenance. And on May 20th, we presented a webinar titled Improve Your Bottom Line, Reduce Metal Manufacturers Processing Energy and Waste, in which we discuss cost-effective practices and technologies to increase energy efficiency and best practices for pollution prevention. We're currently in the process of building our 2020 lineup of webinars, so please be sure to visit the PennTAP website to stay connected and be informed of upcoming PennTAP news, webinars, and workshops. And again, my contact information is here on the final slide. And thank you so much for attending today's webinar. We hope you have a great day and a wonderful Thanksgiving holiday.